Welcome back. Uh, this is part 3 of our NLP class. So, in our last class, what we have seen is how to create a simple model and how to train the model. So, today, what we are going to do is how we can define a model for a logistic regression problem, and then how we can um, optimize that function that we define for the logistic regression model. So, the classical example for logistic regression model is just to find out whether it is going to rain tomorrow or not. So, the problem is finding the y, which is rain or no rain. So, in our linear model in the last class, what we have seen is our objective function or our mapping function f of theta x is defined as theta t x. This is our equation for linear regression model. So, here this theta t x varies from minus infinity to plus infinity. So, but here in our logistic regression model, our y needs to take either 1 or 0. So, it is a binary outcome. How we can convert this linear model into a model which can predict 1 or 0? So, in order to predict this 0 and 1, so how we can modify this function such that it would be predicting the probability of reaching this 0 and probability of reaching this 1. So, the researchers they redefined this function using sigmoidal function. So, this is the linear function. The linear function is converted into the sigmoidal function using the mapping function f of theta of x, which is equal to 1 divided by 1 plus e power minus theta t x. So, this is the same term, that theta t x here and here, and this function converts the linear equation into the sigmoidal function. The sigmoidal function would be looking like this. So, x axis is just this theta t x. So, theta t x may vary from minus infinity to plus infinity. So, the y axis is our this sigmoidal function, which is 1 divided by 1 plus e power minus theta t x. This function actually map the linear function into our so the y axis ranges from 0 to 1. Now, whenever we know this value theta t, when you plug in this theta t x into the sigmoidal function, what we end up is we would be getting the values between 0 to 1. So, this is the conversion, mapping conversion. So, let us assume that this is the central line where the value is 0. So, outside this theta t x is greater than 0, this portion is where theta t x is less than 0. So, whenever we have theta t x greater than 0, we end up having this function which is having a value greater than 0.5. This portion is greater than 0.5 and this portion is less than 0.5. So, this function would have either greater than 0.5 or less than 0.5, greater than or equal. So, this mapping function, the sigmoidal, the beauty of this sigmoidal function is you can see this is the narrow portion where it actually exponentially grow, the value of the y axis exponentially grow and then smoothen out and it becomes very flat. The slope is very low here. It never reaches 0 or it never reaches 1. It would be very closer to 1 and 0, either this side 0.00001, the other side it would be 4.99, sorry, it's not 4 point, 0.49999. So this is how we can have our logistic regression function. Now we know what our mapping function is. So do you remember that what is the scope of this mapping function? The scope of our mapping function is just map all our inputs x to our output y prime. So in between this function will give us the probabilistic value between 0 to 1. So here we just use our threshold y prime is equal to 1 whenever this mapping function f of theta x is greater than or equal to, it depends on the situation of the problem, 0.5 otherwise. So there is just a small change in our mapping function between the logistic regression model and our linear regression model. So what would be the next step? So it would be very similar to our linear regression model. We know that in our linear regression model, what we did, just we need to first define our mapping function f of x, and then we need to optimize our thetas in this mapping function. So how do we optimize our thetas? We optimize our thetas by using our gradient descent algorithm. What does this algorithm does? This algorithm is actually finding out the best value of thetas such that the error is minimum, such that the best theta such that error is minimum. So we would be using the same logic for logistic regression model as well. So in this logistic regression model, we need to find out theta. This is our mapping function. In this one, we have to find out this theta using again the same gradient descent algorithm such that the error or cost function is minimum. Cost function should be minimum. How do we define our cost function here? The definition of cost function is slightly different for logistic regression model. So in our, do you remember the error function for linear regression model? It is actually, error is just squared difference between y and y prime, and then minimize that error. Here instead, how we define the error in logistic regression model is, the cost function is defined as j of theta, and then for all the information in the given input. So let us assume that there are m observations, m is number of observations. For all our observation, so we would be defining cost function which has two components. So one cost component is when y equal to 1, and another cost component is when y equal to 0. So we want to have cost which is minimal whenever our prediction is accurate. So whenever y equal to 1, then we want our mapping function behaves and then produces this y prime equal to 1. So if our mapping function produces y prime equal to 1 during the gradient descent, then cost should be minimal. So then how do we define that one here? Which is just multiply this actual y with the log of our mapping function. Our mapping function here is f of theta of x. Again, when y equal to 0, we want the cost is also 0. Whenever y equal to 0, and when we see this our y prime is equal to 0, that means our mapping function is predicting this y prime accurately. In that situation, we want this cost to be minimum. So how do we define that the second component or second part of this cost function? Here, which it would be looking like this: 1 minus y log of 1 minus this mapping function f of theta of x. So we can see how it works. So we can see, we just to look at this first portion, then which is actually multiplied by 1 divided by m, minus 1 divided by m. So since we have m number of observation, we are just normalizing the value, taking the average value. Here the minus is added, since the entire value would be in negative term. In order to have the cost in positive direction, we are adding the negative sign here. So just look at the first portion and see how it works. So the first portion is when y equal to 1. When y equal to 1, our cost function behaves like y into log of f of theta x. We know what this f of theta x is. Y into log of e power minus theta tx. So now let us assume that this is y equal to 1, and we want this cost value equal to 0, closer to 0, when y prime is equal to 0, or this portion, this mapping function is closer to 0. Whenever 1 divided by 1 plus e power minus theta tx is closer to 0, we want this entire cost function to be closer to 0. How it happens? So when y equal to 1, just substitute these values: 1 log of this entire term is closely equal to 0. This, when it happens, this log of 0, oh sorry, so this would be, oh I made a mistake. So whenever this y equal to 1, whenever this mapping function is closely equal to 0, the log of 0 becomes 1. So what would happen then? 1 into 1 becomes 1. That means cost is high. So because our prediction is not aligned with the actual, our prediction is equal to that, closely equal to 0, but actual is 1. So the cost is high. On the other hand, what would happen whenever y equal to 1 and our mapping function is also closely aligned to theta tx is also closely equal to 1, then this function, when we plug in this value, what would happen? Y equal to 1 and log of this value is closely equal to 1. Then we know that log 1 is equal to 0, and the cost, this part of this cost function becomes 0. So how it would look like is, when you graph it, this portion of the cost function look like this. This is our mapping function, logistic function theta tx, and this is our cost function j of theta. So here this is for y equal to 1. When y equal to 1 and y prime is also equal to 1, this value, this y prime, this is a f of x, this f of x is closely equal to 1, then this will, the cost will be closer to 0. So it's very very minimum. This is our cost function. Y-axis is cost. So cost will be very very minimum. On the other hand, when y equal to 1, but our this mapping function is closer to 0, when it is closer to 0, the cost would be very high. So the function would be looking like this. This is the cost function, the first part of the cost function. Then we will see what happens when y equal to 0. So when y equal to 0, we know the cost function, as the part of the cost function is 1 minus 1 y log of 1 minus this f of theta of x, or this can be rewritten as 1 minus y log of 1 minus 1 divided by 1 plus minus theta tx. So this is the cost function. So we will see what happens here. So here the y equal to 0, but when this value becomes 1, mapping function is closer to 1, what do we want? Do we want the cost to be minimum or maximum? So this is equal to 1, that means prediction is not equal to actual. So we want the cost function to be maximum. When you plug in this value inside this formula, what we have is 1 minus 0 log of 1 minus, this is closely equal to 1, and this portion becomes this log 1, this will be 1. So cost is high. So on the other hand, if the predicted value theta t x is closer to 0, what would happen to this cost function j of theta? This will becomes 1 minus 0, actual is 0, and log of 1 minus this 0, 1 log of 1. So log of 1 is 0. The cost is minimum. So this function works fine for both the conditions, y equal to 0 and y equal to 1. So we can actually show this function in a picture, that or in a diagram, similar way, where this x-axis is mapping function 1 divided by 1 plus theta t x, which varies from 0 to which varies from 0 to 1. Here this mapping function, when this mapping function is here, when y equal to, this is yeah, y equal to 0, in y equal to 0, when this mapping function is also 0, what do we want? We want cost to be maximum or minimum? Yes. So we want the cost to be very minimum. We know that when this is 0 and this is 0, both are in alignment, and we want the minimum cost. So y axis is j of theta, and this is minimum. On the other hand, y equal to 0, but our mapping function gives closer to 1, then the cost would be very very high. Then this function will look like this. So here also we know, now we know what is the mapping function for logistic regression model, and we know what is the cost function, and we will be applying the same gradient descent algorithm to optimize this cost j of theta. The procedure would be same. So I will not go into the derivation of the gradient descent algorithm for logistic regression model. We'll just remember the two equations. One is the mapping function for logistic regression model f of theta of x, which is 1 divided by 1 plus e of theta t x, and second one is our cost function j of theta. One equal to m y into log of f of theta x plus 1 minus y log of 1 minus f of theta x. So, this is our logistic regression model. So, this model works fine to predict any binary outcomes. It works for all type of classification models. So, till now what we have seen is classical examples for linear regression model and logistic regression model. In our next class, what we would be seeing is NLP, real natural language processing model. So, next one is how we can apply this logistic regression model to a sentiment analysis problem. Sentiment analysis problem. See you all in next class. Thank you. Bye.